All right, let's continue with 3.5. What we have from previously, we had a system of differential equations in 2 dimensions. We turn it into an eigenvalue and an eigenvector problem of the matrix. And then we discussed the first case, 2 distinct real. Then we realize, okay, we have 2 straight line solutions, and each one has one of the following cases as a sink, as a source, and as a node. All right. Now, second, we have 2 complex eigenvalues. And what we have from there is, number 1, the complex value actually gives you a pair of complex eigenvalues. So if you do one, it's equivalent to do both. We have the real part, we have the imaginary part, and each one gives us a solution. So the final thing looks like a spiral in for a sink, a center, which is basically a circle, and we have a spiral out, which is a spiral source. And the key to look at is actually look at lambda to see if it's less than 0, bigger than 0, or equals 0. And when I say not lambda, we are looking at the real part of the lambda. A bigger than 0. Okay, and the solution actually looks like e to the at with cosine t, bt, and sine t, bt. Okay, so the cosine and sine part takes care of the rotation, and the real part actually takes care of the shrinking, stretching as they rotate. So A is actually the real part of lambda. Okay, we have 2 more cases left, and we are going to handle them both from here. So that's when we have still real solution, but we have a 0 eigenvalue, or we have a repeated. Actually, let's don't put them together. And the repeated eigenvalue. Okay, so that means we have 1 real, but it's repeating, now instead of 2 distinct reals. You may ask, can we have a repeated complex? For 2 by 2, remember, whenever we have a plus bi, automatically we have a minus bi. So we're not going to have the same complex value repeated for twice, but it has to appear in pairs which are conjugated to each other. Therefore, the moment you're trying to say a plus bi, you automatically include a minus bi, and when you say it's repeat, basically you're just implying a plus bi equals a minus bi. This implies that b equals 0. That means you have a real case, not an imaginary case. All right, so we only have these 2 cases left for 2 dimension. Of course, we study them in the same way. We consider how to solve the equation, and we consider how to quickly see, do we have a sink or do we have a source? All right. So the first one is going to be 0 eigenvalue. Okay. And let's see, does it work? If it works, it passes. If it doesn't work, we think about how to change what we had before. So still, let's start from example and try to see, can we still do the eigenvalue and eigenvector? And the example we have is 2, 2. Okay, very quick computation. We have determinant a minus lambda I equals lambda minus 2, negative 2, positive 3. Should not be this case. Should take out the right thing. Oh, negative 3, 1, 3, negative 1. We have lambda plus 3, lambda plus 1, minus 3. So we have lambda equals 0 or lambda equals -4. Okay. For lambda equals -4, you can do the computation. The final answer is going to be, let me finish it. Okay, let's not skip steps. -3, 1. AB as your eigenvector with -4. So what we have is -3a plus b. All right, both of them give you 3a equals -3b. Let's see. So both give you a equals -b or b equals -a. So what we have is a -a, which is a 1 -1. So this will be the first eigenvector corresponding to lambda equals -4. It's no surprising, but what we care about is actually what will happen to this lambda equal to 0. So what does it do? It gives you I'll keep copying the wrong thing. The y is on the bottom. You just put 0 here. Then that gives you nothing but this. Let's give you b equals 3a from both. Therefore, your final eigenvector corresponding to lambda equal to 0 is a 3a, which is a times 1, 3. Okay, so this will be your eigenvector too. And now if you just do everything we had before, this is going to be c1 e lambda 1 v1 plus c2 e lambda 2t v2. Here's a t. We just have c1 e to the -4t, the first eigenvector, -1, 1. 1, -1, plus c2 e to the 0t, which give you nothing, plus 1, 3. You can even verify there's nothing wrong with it. You just plug it back in. Okay, you verify these two are actually the solution of the original system. Then this will be the solution if you just solve it. From here we can see 0 eigenvalue does not give you any trouble because you can still compute eigenvectors even for eigenvalues. It may look a little bit weird when you have e to the 0t here, but simply it's just a constant. So your final answer is going to be e to the lambda 1t plus c2 times e to the lambda 2t. It's just for the second one, you don't have a e to the lambda case, which is equivalent to e to the 0t case. Okay? So there's no trouble. Just pretend it's, actually you don't even have to pretend, it's just what we had before. The only difference is going to be the phase portrait. Okay, so if your final answer is going to be this, what's going on here? Well, two ways of understanding this. The first one is we do have a real solution, or we do have a straight line solution from 1, -1. And because we have -4, so everything goes in this way. We do have another one from 1, 3. Okay, now we're going to compute how the other solutions are going to look like, right? So think about this. We have one coming towards this way. Now, depending on what we have on this line, if it's this way, then this is going to lean towards this one. If it's this way, it's going to lean towards going away. But now what we have is e to the 0t. What do you mean by that? That means if you start from a point, you just stay at a point. Okay, so one trajectory like that is like that, one trajectory is like that. They don't move. They don't move up or down along this line because you have e to the 0t. You don't get attracted to 0 as t become bigger. You also do not go away from 0. You just stay at there. So on this direction, it's fixed. Therefore, it's almost equivalent to say, hey, before I either go this way or this way, but now I don't go either. Therefore, my next possible solution for a different initial value is going to be this. Do it again. Or this. Do it again. So you can see you are not going to have some trajectories like before, but you are going to have a lot of parallel lines. On each line, if it's in the direction of 1, -1, you got attracted to the middle, to the blue line. But as you go through the process of being attracted to the blue line, you stay parallel to the original 1, -1 because you don't move in this direction or this direction. Okay, so that's basically going to be the phase portrait we have. All right. Another way to think about this is just look at what we have here and try to make it clean. Okay, so what you see here is basically it's a line. Okay, no. Plus a constant. And you know for vector, when you say a plus a constant, this basically means a translation. Or equivalently, we call it a shift in the direction of 1, 3. So basically what you do is you take this line which passes 0, 0. You just shift it towards this direction for a constant. You shift the whole line. Okay, there's no trend on the line. On the blue direction, you just shift the whole line. Okay, so it's either here. If you pick a C2, it's here. If you pick another C2, you pick different C2. It's the same as shifting for different distance from in the same direction. That is towards this. Okay, so that's another way to think about this one. So it's a, how to say, a straight line shifted in other directions. Either way. -1, 1. Okay, that's the green line. Everybody follows the green line. And now that thing, you got a attractor. So everything actually moved to 0, 0. From here, you can see from the bottom to the up, from the top to the bottom. After that, for each solution, you just take this green line and shift in the direction of the orange. Okay, which is 1, 3. But after you shift that, because on the orange direction, you do not have a preference to leave or got attracted, which means you move towards the 0, 0. Therefore, they're just parallel lines. They do not bend towards the 0, or they don't bend towards infinity either. Okay, so two straight line solution for 0 eigenvalues. The only difference is this time you do not have both direction coming towards infinity or coming towards 0. Okay, so we got one more cases. That's done. Now we want to talk about the next one, which is the repeated real eigenvalues. This one is going to be a little bit more complicated. After that, everything is done. Let's still see it from an example. All right, so now let's take A out and compute the determinant of A minus lambda I in order to get the characteristic. Okay, and what we have is lambda plus 2 square minus 0 equals 0. So clearly from here you can see you have lambda equals -2. Okay, now so far so good. Lambda equals -2. Can you find an eigenvector? Well, from here you can see the first one tells you b equals 0. Therefore, the eigenvector b equals 0. So you have AB, which is A0, which is A times 1, 0. So you have this eigenvector corresponding to lambda equals -2. And you stop here because you do not have a second which is the distinct real eigenvalue. So far, there's no trouble. But now the next thing becomes trouble because you want this. All right. And if you keep continue, you have C1 e to the negative 2t, 1, 0, plus C2 e to the negative 2t, 1, 0, because they have the same eigenvalue. Of course, they have the same eigenvector. But then if you think about that, that is nothing but C1 plus C2 e to the negative 2t, 1, 0. So even though it seems like you have two constants that you can vary, but actually they got merged into one constant. But in order to solve this initial value problem, you know you need to have two distinct, two real constants. Okay, so you are still in one short of another solution. You need two solutions. That's where things goes wrong. All right, so this cannot work. The reason this doesn't work is because the moment you write this down, now this time we don't have lambda 1, lambda 2. We just have one lambda. We just have one v. Okay, you're missing a second part. You need another part. This part should contain C2, of course. This part should contain a vector. Okay, and this part should contain a solution. So your job is try to figure out what should you put here in order to make this one work. All right, and the thing you should put here is basically going to be a function of t, okay, times a vector. Let's call it a vector. Let's call it w. All right. So w is easy to do once you know the function because you can plug in and try to somehow figure out what v is. But what function should you put here? There are two ways to do it. The first way is actually solve the case, which we already know, to get a hint of what's going on here. So we already know if you solve everything in terms of eigenvalue and eigenvector, we got trouble. But then a second thought, I do know what this is. This is a partially decoupled system, right? So I can cheat a little bit, which only works for this case, by the way. Okay, so we got y prime equals negative 2y, y equals e to the negative 2t with a constant. So far, no problem. This is exactly what we got from the eigenvalue and the eigenvector later. Cool. Now x prime equals negative 2x plus a y. Okay. And then after that, what we should do is we should put everything here. Something is wrong. Negative 2 plus... Oh, it's all right. Yep. Okay. Equals c1 e to the negative 2t. Now x numerical integrator, an integrating factor, mu equals e to the integration 2 dt. X e to the 2t, x prime plus cancel. Yep, the multiply equals 0. Now e to the 2t, x prime equals c1, e to the 2t, x equals t plus c1, c1t plus a c2. So finally, your x equals c1 t e to the negative 2t plus c2 e to the negative 2t. From here, you can see, yes, we do see the familiar e to the negative 2t. And just for this example, it suggests that we should also include a term of t e to the negative t. So this is a very strong candidate for ft, at least for this one case. You may have other metrics which do not give you the same answer. But for this case, we already solved it. So this one is definitely a strong candidate. Okay. That suggests you should take your y equals this. Lambda t v 1, or let's call it v0. And it suggests the missing second part is going to be t to the lambda t, which uses the same lambda, but you do have a t, okay, to make them linearly independent. with this. That's what this one suggests. Okay? That's one way of doing it. Another way to think about it, actually this term is great. Why? Because remember, your final goal is try to find a y satisfying y prime equals ay, right? E to the lambda t is very good. Why? Because the derivative and itself satisfies a relationship that is, it's nothing but a linear combination of itself, which is basically the right-hand side. Your derivative should be related to yourself. Okay. Now what about this one? Well, the derivative of that one has the same property. It depends on itself. But by product rule, it also depends on another function. But nicely, if your solution already have this from the previous solution, you can see you do not create additional terms. So which make this whole thing possible. Now if you think about it, change something to something else. For example, if you you let your y has a term which is sine t somewhere, right? Then your y prime is going to have some term which is cosine t. Now if you want to set up y prime equals ay, what you have on the left-hand side is you are going to have sine t, cosine t. On the right, you have sine t, maybe with some constant multiple, or with some plus or whatever, right? But there's no way you can make a cosine t out of sine t. So what you want to do is you want to put in a function here, and make sure that the function you put in, if you take the derivative, it only requires itself and something you already have from the first equation, which is this, first solution, which is this. Then, by somehow take 2 times this plus 3 times this, you will somehow be able to make adjust the right derivative on the left-hand side. Okay? Not any function will work. Only the functions that if you take the derivative of itself, you will only have itself plus something you already know. Then, by timing a matrix on it, which means taking a possible linear combination, you will be able to weight y prime in order to satisfy this equation. All right. So with these 2 arguments, it's settled, at least temporarily, that this may be promising, that the second one should look like this, which is exactly the first one, but adding another t. Now before we go ahead and do it, because now we have everything except for v1. v0 is your eigenvalue, you just did it. E to lambda t, you already did it. Okay. What you're missing is actually this v1. Moreover, later we will see your v0 and v1 cannot be decomposed so clean to have a constant times another constant, because you may very possibly to have something like this. Okay, and after some decomposition, you will be able to make them to be like c1, c2, e to the lambda t, plus c1, 0, for example, and e to the lambda t. And there's no way you can actually further decompose them, okay, to put all the c1 together and c2 together. So in order to make this happen, what we do is we kind of absorb this constant into v0, and you absorb this constant into v1. So before, when we finish something like this, the next step we do is actually change this to that, and we say this is going to be our eigenvector. Now all we do is actually we don't do this. We just keep this one as our eigenvector. Okay, with a freely varying constant inside, but it's actually the same as taking it out. It's just for this time maybe you are not able to take it out. All right, so this is where we start after the guess. Our solution looks like this. Moreover, v0 and v1 contains c1, c2 inside. That's what we got. All right. Now our job is try to find v1 and v0. What are we going to do? Well, we do know y prime should equals ay. After all, it's the solution. And if the y looks like this, you can compute y prime yourself. Okay, this one is going to have v1. Okay, remember v1, v0 does not have t, but you are going to have a product rule. times lambda plus e to the lambda t. Okay. You take the derivative of t, or you take the derivative of e to the lambda t, which produce another lambda. Now after that, what we can do is we can clean things a little bit and put everybody with e to the lambda t together. Okay, that's this term and this term. Okay. Now the other one together, we put lambda v1 there. That's what we got from y prime. All right. What we should get from ay, and they should be the same, is just to simply apply a to the y. So you got a e lambda t v0 plus a t e lambda t v1. Let's clean things a little bit. To put e to the lambda t here, we got lambda v0 plus t e lambda t a v1. Okay, this should work for any t. Therefore, this part should equal this part, and this part should equal this part. So if we write all the red relationship down, we have AV1 equals lambda V1, indicates V1 is the eigenvalue, eigenvector, sorry, of lambda. In our case, that's the 1, 0 we computed. For second, we have lambda V0 plus V1 equals, this is A, equals AV0. Now, how do we get V1? We get it from the eigenvector. Our job now is try to get V0, assuming we already know V1 from step 1. Then we have lambda I minus A, if we move V0 on the other side, equals V1. All right. That's the relationship we're looking for. If we just plug in whatever we assumed of the format of the solution into the original system, and try to find, then your V1 and V0 should have this kind of relationship. Okay, so let me write down what we just did. We started from repeated eigenvalue. Okay, then we guess y equals this, because we only have one lambda. There's no lambda 1, lambda 2 anymore. Okay. Now our first job is find the V1, because V1 satisfies this. Therefore, V1 is an eigenvector. You know eigenvalue, you can find one eigenvector. That's step 1. Okay, totally works. The sad part is you only have one answer, because you only have one eigenvalue. Where are you going to find the second one? Now, we find the second one by solving this. You know lambda, you do know A, okay. And you do know V1 by solving the eigenvector. Therefore, you can find V0 by yourself. And once you finish, just plug both back into this. You have the solution. That will be the fundamental fact we need in order to solve systems with repeated eigenvalue. Okay, so let's go over the process again. We start by doing the eigenvalue and eigenvector, which is fine, but we need 2. We only have 1, so we have a missing part. For that missing part, we did 2 attempts. We solve this problem as a decoupled system. We find probably that term should be t times e to the lambda t. Okay. Then we actually go from the argument. We say, well, you have to create some terms when you take the derivative, and that term should only include yourself and the term you already got. Then it seems like t times e to the lambda t is a good choice. All right. Then it's settled. We do write everything as e lambda t plus t e lambda t. There are 2 different terms. Now we just need 2 vectors to tell us what's going on. We name them v0 and v1. After that, what we did is we plug this y, this format of y, pretending we don't know v0 and v1, into the original differential equation. Solved it. We find that in order for them to be the same, the e lambda t term has to match, and the t times e to the lambda t term has to match, which implies that the red block equals to the red block, the blue block equals the blue block, and the red block tells you a simple truth, that is your v1 should be calculated from finding the eigenvector, and your v0 should be calculated from that formula after you know how to find v1. Then we wrote them all down into this recipe. This is how we're going to do it. Okay. Let's finish the problem. Now, we started from y prime equals -2, 0, and 1. Okay, y. First job, try to find lambda. We already have this one at the beginning, so I will skip some steps. After that, we do have equals. This implies p equals 0. Therefore, your eigenvector for lambda equals -2 is going to be a0. Okay. Before, what we should do is we should take this one and change it to be a times 1, 0, and only take this part. For this time, remember we kind of merged the constant into the vectors, and they may not be separable. Therefore, we just keep things in this way. We don't factor them out. And here, we get our first constant. We name it C1. Okay, just change A to be C1. First free constant. And according to what we have here, this is what? This is what we had for V1. This means this will contribute to this term. That's your V1, what you just find. Now in order to finish, we need this part. How do you get that? We get it from lambda I minus A, V0 equals, let me make sure I'm writing the right thing. Okay, that's why I feel weird. This is A minus lambda I, because you want to move this one to the other side. Okay, so this, you just need to switch the order. I put the wrong order there. Okay. All right, A lambda S I equals V1, but V1 you already know what it is. Okay, minus lambda. Yeah, let's not do this. This is your A minus lambda I. Okay, we got -2 minus lambda 0. Okay, AB. This time we're looking for V0. Okay, equals V1. V1 is what we just got, C1, 0. Where C1 is a free constant, which means as your V1 change, your V0 is going to change. That's why we say, well, this time you cannot write V0 and V1 out with a C1, C2 outside because they are kind of related. Okay, but what we have here is lambda is of course -2. So you have 0, 0, 1, 0. A, B equals C1, 0. This implies A equals C1, B equals, no, 0 equals 0. Okay, This basically implies V0 equals A, B, but then your A has to be replaced by C1, which is determined by V1. Okay, your B here can change for free because you can see there's no restriction on B. And finally, for convention, we change it to another constant, which we name C2. And what we want to say is your V1 is this one, and your V2 seems arbitrary, but actually your V2 changes. The first component of your V2 should change with your V1. Sorry, this is V0. Okay. But the second one is free. So in this case, we have two free constants. And your final answer is going to be y equals e to the lambda t plus t e to the lambda t. Your V1 comes here. Your V2 comes from here. And you can try yourself. This cannot be written as C1 V0 C2 V1 case. That's why we actually merge this constant into the original vector. If you want to write it out, your x looks like C1 e to the negative 2t plus t e to the negative 2t C1. C1. Oh yes, that's your x. And your C2, your y is going to be e to the negative 2t C2. Yes, okay. Somehow. This is bad. Okay, this is a long process. I made one minor mistake. That is when I got here, I should have B equals C1. Before I said it's going to be A. Let's change it back. So, switch this. Now it looks like the right answer. If you check, this is exactly what we got from, solving everything from the decoupled case. And this one is going to be C1 e to the negative 2t. That's your x, that's your y. Okay. All right. So this can be confusing. I would suggest you to read these examples after class by yourself and then close the notes and do this example fully by yourself. Okay. If it's necessary, do it for twice or 3 times until you see what's going on here. Okay. All the logics are easy to follow. They don't feel so natural. You cannot see them right through. So do the computation and try to see why do we have these two equations. And once you have these two equations, you can trust them. Then the procedure should be find V1 first and solve V0 from V1. Okay. And that's why we are doing all the procedures afterwards. The rest is just trying to do the procedure. The only part you probably want to be careful is, I know you had a habit, which is every time you see something like this, you just factor it out to be this. But for now, you should keep it. Keep this constant and bring this constant into this equation. And your final answer of V0 should also depend on the first constant. And this time, V1 and V0 are closely connected. So you cannot easily separate them. Okay? I don't think going over another example is necessary because it's basically repeating the same process with a different constant. This is what we have for repeated eigenvalues. Okay. Here, of course, I can give you an alternative approach, which is especially useful when you solve initial value problem. Okay. So let's say you already have this, and you have an initial value. So what are you going to have? You are still going to have this y equals e to the lambda t v0 plus t e lambda t v1. That's your final solution. And then you go ahead and try to solve for v1, v0. That's certainly one way. Okay. But another way, if you try to think about it, if you plug in 0, what are you going to get? You are going to get v0 plus 0 e to the lambda, which is, so you are going to get e to the 0, which is 1, v0 plus 0 due to the t here, times everything, so 0 vector. This implies v0 should equals x0, y0. So automatically, for initial value problem, you can get v0 for free. You don't have to go through the whole process. And if you go through the whole process, you will get the same thing. So you get v0 for free from the initial condition. But this still works. This relationship should still work, right? Before you know v1, you find v0 by solving a linear system. But now what you can do is you can know a v0 and then go ahead and try to solve for v1. So that's another D tool, which you solve v0 first and the v1 second. Okay, so I will try to show you how to do this again. We will skip some steps. Okay, so we have y prime equals ay. Okay, now we already know the final answer is going to be this. So we still do all the job we need to do in order to get the eigenvalue. Once we know eigenvalue, we have the solution. We just need these two vectors. But now we know one simple fact. That is, this one should work for any initial value. So if I plug in 0, I should really just get v0. This should be x0, y0 for any possible eigenvalue. Or you can equally say this can be equal to c1, c2 for any free constant. This time you just know what the free constants are, but still. Okay. Then what you can do is you can do a minus lambda I times v0 to get your v1. But it's not solving a linear system. This is just a matrix. Multiply with a sum vector you already know, which is going to be c2, 0. Okay. In this way, automatically you can write down your solution. You name these two by yourself because you know these two are free. Because it's any possible initial values. But once this one is free, your second one is going to depend on the first one. And you can verify this is exactly the same as what we just get. Okay, except we exchanged the name of C1 and C2. Okay, so this is the alternative approach. And again, the key factor here is, number one, the solution looks like this. That's a key assumption. That enables that your V0 is just the initial condition. And the second, you're still relying on this fact. But instead of knowing V1 to solve V0, you can also know V0 to solve V1. Okay, so which approach do you prefer? Pick whichever. If you go with the second approach, you don't even have to worry about what the eigenvalue or what the eigenvectors are. They are just two vectors, okay, which worked. And by coincidence or not coincidence, the second one happens to be the eigenvector, but you really don't care. All right, that's what we have for repeated eigenvalue in terms of solving it. Of course, finally, we want to know the phase portrait. So what is a phase portrait? Well, let's take this one as a particular example. Do I want to do this? Maybe. All right. Okay. Now we'll let t goes to infinity. What's going to happen? Several things. Number one, y goes towards 0, 0, because both term goes to 0, 0. For this one, you have t divided by e to the negative 2t. So this one is going to be dominant, the one on the top. So this one is also going to be very close to 0. That's why you got 0, 0. Okay. Second, as t goes to infinity, this one is way bigger than this part, because you have another t there. Okay, so this part are equal, but this one has an additional part. Therefore, when t is big, you will say the majority or most of the solution will stay on this direction. Okay, now what do you mean by that? That means we have C2, 0, which is where we got the eigenvector, remember? So that's going to give you this straight line solution. Okay. Now, other solutions will not follow this straight line solution, of course. But when t is big, which means when everything is very close to 0, 0, they are going to be very close. They come in this way, and this way, and this way. Almost parallel, almost very close to this one. This gives you something like a spiral. That can only happen in this case. Because as your t become big, this one is almost at this straight line. And the reason is because the t part, okay, and then almost the same as the straight line. Okay, similarly, from this direction. They cannot approach like that. Okay, they have to follow very close to the straight line there. Because when t is big, this part dominates, which stay on this straight line. So you will see a trajectory like this. Okay? Let's plot it. That's exactly what we got. So this straight line here is where your v1 is, which we get from AV equals lambda v. That's the eigenvector. Your solution will not follow the eigenvector unless it's a straight line solution. But when t is huge, when t is big, when you are very close to 0, 0, everybody approaches towards 0 in the direction of the line. Almost. Okay, it's still not quite the same, but almost the same. So that's what we get from the phase portrait of lambda, repeated lambda value. So if we think about it, we basically had everything. Okay, we have the first case, 2, lambda 1, lambda 2, 2 straight line, and 1 in, 1 out. We have 2 complex with a plus minus. So what we have is spiral sink, spiral source, and center. This is going to be lambda 1, lambda 2 less than 0, and lambda 1 less than 0, lambda 2 bigger than 0, all the other way. Okay. Number 3, we have 0 eigenvalue, which give us a straight line solution, either sink or source, and a lot of parallel. And each one is going to be the same as a sink or source, because basically in this direction it doesn't move at all. Okay, so therefore we don't even have to worry about it. Finally, for repeated values. Okay, then what we really have is something like this. That's one straight line solution in terms of v1 and lambda. Okay, and then the other part is going to be spiraling in, not spiraling, but you know, approaching 0 in the straight line solution direction, or it's going to be leaving. In a direction. Okay, the difference between this is lambda bigger than 0, this is lambda less than 0. Okay, so two things I want to say. Number one is you only have one lambda, and one is this, the other one is this. So if lambda is less than 0, both are shrinking. If lambda is bigger than 0, both are stretching. So we don't have to worry about, you know, which one goes to where. We will always have the same case. It's either all coming out or it's all coming in, even on a straight line. Okay. Second, what's the difference between this one and the spiral? The difference is here. If you have a spiral, you can actually go here, okay, but you can also cross this one again. Okay, this is spiral. But this one, because this is a horizontal asymptote, as t becomes bigger, you are going to be very, very close to what's going on with the straight line. So you can only go here, but you could not go across. This is not going to happen. You're touching your horizontal asymptote, basically, if you do that. Okay, so this will be what we had for repeated. So technically, it's not a spiral, because spiral can actually rotate many times and cross your straight line for many, many times. This one, you cannot cross your straight line solution, because that's basically your, we won't call it horizontal asymptote, but that's basically your asymptote, which you cannot go cross. That's all the cases we have. Exercise. What about, and you think about it, if you have repeated and also 0 eigenvalue? So not only you have a 0 value and you have a repeated 0 value, you don't have a, you certainly won't have something as nice as this. Okay, how are you supposed to solve it? And you can think about systems. Number one, this system is not too interesting, but this is certainly one system you can do. But basically, you just have your x derivative and y derivative are both 0. Therefore, your solution is a point. Okay, that's not going to work. But now with knowledge from linear algebra, we do know this one is going to give you a repeated 0 solution. Okay, solve it. And hopefully you can write a summary for yourself. How do you describe what's going to happen for repeated 0 eigenvalues? All right. That's everything about repeated and 0 eigenvalues, and that's basically everything we have for chapter 3 already. Probably I didn't switch the screen. Did I? Yeah, maybe. I think you can compare to the notes because you're going to receive the notes in the end. So I don't remember when I stopped switching. You can figure out by yourself. All right, that will be all.